You think you know what's impossible? A wall is a wall, particles bounce back, energy barriers hold, but down at the smallest scales, reality doesn't care what you think is possible. A particle approaches a barrier it shouldn't cross. Classical physics says no. Quantum mechanics says, watch this. The particle vanishes from one side and reappears on the other without ever traveling through the space between. No explosion, no force. It just tunnels through solid matter like a ghost walking through brick. This is quantum tunneling. And it's not hiding in some lab experiment. It's happening in your cells right now. It powers the sun. It destroys computer chips. It causes cancer. It built the atomic bomb. And every second of every day, particles in your body are punching through walls they have no business crossing. If you value documented physics and quantum mechanics, history like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. Also, this script is researched and factual using sources from physical chemistry, chemical physics, published January 2021, examining Watson-Crick tautomerism in DNA-based pairs, and ACS Nanovolume 15, published December 2024, documenting the 2025 Nobel Prize in Physics for macroscopic quantum tunneling in Josephson junctions. Now, back to the information. 1928, George Gamow sits at his desk facing a problem that makes no sense. Uranium nuclei spit out alpha particles. Helium nuclei. 2 protons, 2 neutrons bound tight. But here's the thing. The alpha particle inside the nucleus has maybe 5 million electron volts of energy. The Coulomb barrier holding it in 26 to 30 million electron volts. Classical physics says that particle is locked inside forever. It doesn't have the energy to climb out. But uranium doesn't care about classical physics. It decays anyway. Half-life, 4.5 billion years, but it happens. Gamow sees the answer in the new quantum mechanics. The alpha particle exists as a wave function. It spreads out. And when a wave hits a barrier, it doesn't just stop dead. A tiny piece of that wave leaks through. On the other side of the barrier, that leaked wave represents a probability. The probability that the particle just appeared there, without climbing, without smashing through. It tunneled. Gamow works the math. The probability depends on 3 things: barrier height, barrier width, particle mass. The exponential decay is brutal. Make the barrier twice as wide and the tunneling probability drops by orders of magnitude. That's why uranium takes billions of years. The barrier is thick, but it's not infinite. Every so often, an alpha particle's wave function pokes through and boom, decay event, same month. Edward Condon and Ronald Gurney publish independently, same answer. They write one line that lands cold. Aye. Disintegration is a natural consequence of the laws of quantum mechanics without any special hypothesis. No magic, no instability, just waves doing what waves do. Within months, the physics community has proof. The theory reproduces the Geiger-Nuttall law. That's the empirical rule Hans Geiger and John Mitchell Nuttall discovered in 1911. It says short-lived isotopes emit high-energy alpha particles. Long-lived ones emit weak ones. The relationship is exponential and tight. Gamow's tunneling math spits out that same curve from pure theory. Polonium-210, half-life 138 days. Decay energy 5.4 million electron volts. Uranium-238, half-life 4.5 billion years. Decay energy 4.3 million electron volts. The difference? Barrier thickness and probability. Polonium's nucleus is smaller. The barrier is narrower. Tunneling happens more often. Uranium's barrier is wider. The alpha particle rattles around inside for eons before it slips through. The math fits graves and mass spectrometers and decay chains across the entire periodic table. Tunneling isn't theory, it's measurement. Fast forward, 1957, Tokyo, Sony Corporation. A 26-year-old physicist named Leo Esaki is doping semiconductors, heavily. He's pushing dopant concentrations to 10 to the 19th atoms per cubic centimeter. That's absurd. Normal diodes use maybe 10 to the 16th. But Esaki wants to see what breaks. He fabricates a p-n junction, heavily doped p-type germanium on one side, heavily doped n-type on the other. The junction is 10 nanometers wide. 10, he applies a small forward voltage. Current flows, expected. He increases the voltage. Current increases, also expected. Then the current drops. Voltage goes up, current goes down. Negative resistance. That's not supposed to happen. Esaki checks his equipment. Everything works. He checks again. Same result. The current peaks at a certain voltage, then falls into a valley before climbing again as a normal diode. He realizes what's happening. The heavy doping has pushed the conduction band and valence band into overlap. At low voltage, electrons on the n side align with empty states on the p side. They tunnel straight across, quantum tunneling, through the 10 nanometer barrier. As voltage increases, the bands misalign, fewer states line up, tunneling drops, current drops, negative resistance. That curve is pure quantum mechanics operating in a macroscopic device you can hold in your hand. August 1957. Esaki and his colleague Yurko Kuroso file the results. By 1960, Sony is manufacturing tunnel diodes. General Electric follows. The devices work at microwave frequencies, 5 gigahertz oscillators. They're small, fast, radiation resistant, low power. They survive nuclear environments that fry transistors. They last forever. Esaki tests diodes from 1960. 50 years later, they still work. In 2013, he publishes shelf life data. The tunnel current dropped 0.25% in half a century. That's from a 0.25% widening in the barrier width. Atomic scale drift over 50 years. The diodes are effectively immortal. 1973. Esaki shares the Nobel Prize in Physics with Ivar Giaever, who found tunneling in superconductors, and Brian Josephson, who predicted Cooper pair. Tunneling. 3 men, 3 types of tunneling. 1 prize. Josephson's work opened a different door. 1962. Cambridge. Josephson is 22 years old, second-year graduate student. He's taking a course with Philip Anderson on sabbatical from Bell Labs. The course covers broken symmetry in superconductors. Josephson gets obsessed. He wonders if Cooper pairs can tunnel, not single electrons. Pairs? 2 electrons bound together in a superconducting state. He works the math. The answer is yes. If you sandwich a thin insulator between 2 superconductors, a supercurrent can flow across the barrier with 0 voltage. 0. The current depends on the phase difference between the superconducting wave functions on each side. Change the phase and the current changes. Apply a voltage and the phase oscillates. That creates an AC current. The frequency? 483.6 gigahertz per millivolt. Exact. Reproducible. Universal. Josephson submits the paper to Physics Letters in June 1962. He's uncertain. The journal is new. Physical Review. Letters is more established, but he's not confident. John Bardeen, already a Nobel winner, reads the paper. He's skeptical. Publicly skeptical. But experiments start rolling in. January 1963. Anderson and John Rowell at Bell Labs publish in Physical Review Letters probable observation of the Josephson superconducting tunneling effect. They've built the junction, 2 superconductors, thin oxide barrier. They apply voltage. They measure current. The curves match Josephson's predictions exactly. Bardeen comes around. He later nominates Josephson for the Nobel. 1973, Josephson gets the prize, same year as Esaki, age 33. But the Josephson junction doesn't stop there. 1984, University of California, Berkeley, John Clark's lab. Clark is another student of Brian Pippard, same as Josephson. Clark is working with Michel Devoret and John Martinis. They're pushing Josephson junctions into extreme conditions, below 50 millikelvin. That's 0.05 degrees above absolute zero. They're filtering out noise, environmental vibrations, electromagnetic interference, thermal fluctuations, everything. They want to see if a macroscopic system can behave quantum mechanically. A Josephson junction contains billions of Cooper pairs. Billions. That's not a single atom. It's a chunk of matter you can see. They cool the junction. They apply microwave pulses. At zero bias, they measure the energy levels. The levels are quantized, discrete steps. The junction isn't behaving like a classical LC circuit. It's behaving like a quantum harmonic oscillator. The phase difference across the junction is a quantum variable. It exists in superposition. The junction tunnels between discrete energy states, macroscopic quantum tunneling. Clark Devoret and Martinis published in 1985. The paper detonates. It proves that quantum mechanics works at scales far beyond atoms. The junction is large. The system is engineered. And it obeys quantum rules. October 2025. Stockholm. The Royal Swedish Academy of Sciences awards the Nobel Prize in Physics to Clark Devoret and Martinis, both for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit. The work is 40 years old. It's now the backbone of superconducting quantum computing. Every qubit in a superconducting quantum computer uses Josephson junctions. The tunneling mechanism lets qubits flip between states. Google's Willow chip, announced December 2024, uses thousands of Josephson junctions. It achieves quantum error correction. It solves calculations in 5 minutes that would take classical supercomputers 10 to the 25 years. All built on tunneling, predicted by a 22-year-old in 1962. Now shift gears. 1981, IBM Zurich Research Laboratory, Switzerland. Gerd Binnig and Heinrich Rohrer are trying to measure surface conductivity on a local scale. They need to probe areas smaller than 100 angstroms. Existing tools can't do it. They build something new, a needle, tungsten, sharpened to a single atom at the tip. They mount it on piezoelectric crystals. The crystals move the needle with angstrom precision. They bring the needle within a few angstroms of a sample surface, close, not touching. They apply a small voltage between the tip and the sample. A current flows, quantum tunneling. Electrons jump from the surface to the tip. The current is exponentially sensitive to distance. Move the tip 1 angstrom closer and the current increases by a factor of 10. The feedback loop is simple. Measure the current, adjust the tip height to keep the current constant. Scan the tip across the surface. Record the height adjustments. That's a topographic map, atomic resolution, March 16, 1981. Late night. Binnig can't stop staring at the screen. They've imaged a gold surface, 100 angstroms square, individual atoms, clear, sharp, actual atoms. He writes later. It was entering a new world. They call it the Scanning Tunneling Microscope, STM. They publish in Physical Review Letters, July 1982, Surface Studies by Scanning Tunneling Microscopy. The first image is rough. They have to interpolate lines to make it visible, but it works. They refine the design. By 1983, they imaged silicon 1117 by 7 reconstruction. That structure had been a mystery for years. The STM solves it in one image. The surface science community takes notice. Fast. Within 2 years, STM labs are spinning up worldwide. Binnig and Rohrer don't stop. 1986, they developed the atomic force microscope with Calvin Quate, AFM. It doesn't need conductivity. It measures force. That opens biology. Soft materials, insulators, liquids. October 1986, Nobel Prize in Physics, Binnig and Rohrer, 5 years after the first experiment. That's the fastest path from discovery to Nobel in modern physics. Ernst Ruska shares the prize. He invented the electron microscope in 1933. He waited 53 years. The STM is that important. It births nanotechnology, direct manipulation of atoms, April 1990. Don Eigler and Erhard Schweitzer at IBM Almaden use an STM to move individual xenon atoms on a nickel surface. They spell IBM, 35 atoms. The image becomes the most famous in nanotechnology history. The STM isn't just seeing atoms, it's pushing them. Tunneling current gives enough force to slide an atom across a surface. One atom, one push, controlled, reproducible. We can build things one atom at a time because of quantum tunneling, but tunneling isn't always helpful. Semiconductors, Moore's law. Every 2 years, transistor counts double. Chips get smaller, gates get thinner. By 2000, transistors hit the wall, gate oxides drop below 2 nanometers, electrons start tunneling through. The gate is supposed to control current flow by raising or lowering a barrier. But if electrons tunnel through the barrier, you've lost control. Leakage current, power drain, heat. The chip burns itself. Intel reports in 2003 that leakage current in 90 nanometer chips accounts for 40% of total power consumption. 40, that's tunneling. Unwanted, destructive. The industry fights back. High K dielectrics. Replace silicon dioxide with hafnium oxide. Thicker dielectric. Same capacitance. Less tunneling? It works for a while. But transistors keep shrinking. 14 nanometers, 10 nanometers, 7 nanometers, 5 nanometers, 3 nanometers. Now we're at 2 nanometers in development. The barriers are quantum scale. Tunneling is everywhere. Some engineers flip the problem. Instead of fighting tunneling, use it. Tunnel field effect transistors, TFETs. The channel is controlled by tunneling current. Apply a gate voltage, lower the barrier, electrons tunnel through. The sub-threshold swing gets steep. The transistor switches faster with less voltage. A European project in 2024 demonstrates TFETs that operate at 0.2 volts. Standard MOSFETs need 1 volt. That's 80% power savings. Scaling to VLSI is hard, but if it works, tunneling becomes the answer, not the problem. Now the biology, 1963. Per Olaf Loden publishes a paper, Proton Tunneling in DNA and its Biological Implications. He argues that hydrogen bonds between DNA-based pairs can undergo proton transfer via tunneling. A proton shifts from one side of the hydrogen bond to the other. That changes the bond length. The base pair tautomerizes, canonical form to rare form. When DNA replicates, the polymerase enzyme reads the bases. If a base is in the rare tautomeric form polymerase picks the wrong complement, adenine pairs with thymine, guanine pairs with cytosine, always, unless a proton is tunneled. Then guanine looks like adenine. Polymerase inserts thymine instead of cytosine. Point mutation. Loden's hypothesis sits for decades. Hard to test. You can't watch a proton inside a DNA helix, but computational power grows. 2021, Louis Slocum and colleagues at the University of Surrey publish in Physical Chemistry, Chemical Physics, the quantum and classical effects in DNA point mutations, Watson-Crick tautomerism in AT and GC base pairs. They model the hydrogen bonds with high-level density functional theory calculations. They calculate energy barriers, tunneling probabilities, temperature effects. The results are clear. For guanine-cytosine pairs, the reverse barrier is large. If a proton tunnels from cytosine to guanine, it stays there long enough to matter. For adenine-thymine pairs, the reverse barrier is tiny. A tunneled proton immediately tunnels back. No mutation. But GC pairs? Vulnerable. Right before DNA replication, the strands unzip. The hydrogen bonds break. If a proton is tunneled just before unzipping, it gets locked on the wrong side. Polymerase comes in, reads the base, inserts the wrong nucleotide. Mutation. The paper calculates that quantum tunneling contributes several orders of magnitude more to proton transfer than classical over the barrier hopping. Several orders. Tunneling isn't a minor effect. It's the dominant mechanism. Watson and Crick saw this coming. They proposed spontaneous tautomerization as the source of point mutations in their early DNA papers. But they didn't have quantum mechanics in the model. Now we do. Experiments are harder. You need to watch protons in real time. One approach. Deuterium. Deuterium is hydrogen with a neutron, twice the mass. Tunneling probability drops exponentially with mass. If you grow cells in heavy water, deuterium oxide instead of regular water, the DNA incorporates deuterium. The bases still tautomerize, but tunneling slows. If tunneling is the mechanism, mutation rates should drop. That's the test. Antonio and Virginia at Surrey's Leverhulme Quantum Biology Doctoral Training Center are running it now. Grow bacteria in D2O, measure mutation rates. Compare to H2O controls. Early results suggest the effect is measurable, not published yet, but if it holds tunneling is the engine of genetic mutation, every cancer, every evolutionary adaptation, every inherited disease caused by a point mutation, quantum tunneling wrote the code. Enzymes use tunneling too. Enzyme catalysis. The reactions that keep you alive? Breaking down food, building proteins, copying DNA, repairing damage. Classical transition state theory says enzymes lower activation energy by stabilizing the transition state. But kinetic isotope effect experiments show something else. Replace hydrogen with deuterium in an enzyme substrate. The reaction slows, a lot, more than classical theory predicts. That's tunneling. Protons and electrons tunnel through activation barriers. Soybean lipoxygenase, that enzyme transfers hydrogen. Deuterium substitution slows the reaction by a factor of 80. Classical kinetic isotope effects max out around 7. The rest is tunneling. The enzyme active site is structured to keep the donor and acceptor close. 10 angstroms or less. The barrier is thin. The proton wave function leaks through. Reaction happens faster than thermodynamics allows. Mitochondrial complex 1. That's the first enzyme in the electron transport chain. It pumps protons across the inner mitochondrial membrane, generates the gradient that makes ATP. The whole thing runs on tunneling. Electrons tunnel through iron-sulfur clusters. Protons tunnel through hydrogen bond chains. A recent paper in Biointerface Research and Applied Chemistry, Volume 14, Issue 4, published 25 models. The tunneling probability across 3 barriers in complex 1. They solve the Schrödinger equation numerically. Barrier 1. Tunneling probability ranges from 10 to the minus 30 to near 1 depending on energy. Barrier 2, 10 to the minus 64 to near 1. Barrier 3 similar. Those are huge ranges. The system is tuned. Certain energy levels tunnel easily, others don't. The enzyme uses quantum selectivity to control proton flow. You breathe because of quantum tunneling, then there's the sun, fusion, hydrogen nuclei smash together, overcome electrostatic repulsion, fuse into helium, release energy. The temperature at the sun's core is 15 million Kelvin. Sounds hot. It is, but it's not enough. Classical physics says protons need 10 million electron volts to overcome the Coulomb barrier. Thermal energy at 15 million Kelvin is 1.3 kilo electron volts. Not even close. The sun shouldn't burn, but it does. Quantum tunneling. Protons don't need enough energy to climb over the barrier. They just need enough energy to get close. Then the wave function tunnels through. The probability is tiny. The reaction rate is slow, but the sun is huge. 10 to the 57 hydrogen atoms in the core. Even a tiny probability gives 10 to the 38 reactions per second. That's enough. The sun burns because quantum mechanics breaks the classical energy limit. Without tunneling, stars don't ignite. Planets freeze. Life doesn't exist. Tunneling wrote the universe. But fusion on Earth is harder. Controlled fusion, reactors. We need to replicate the sun at lower temperatures. That means higher tunneling rates. Deuterium, tritium fusion. The cross-section peaks at 50 kilo electron volts. Still way above thermal energy at any temperature we can sustain. The plasma has to be hot enough that the high energy tail of the velocity distribution gives significant overlap with the tunneling regime. 100 million Kelvin, 10 times hotter than the sun's core. ITER. The International Fusion Reactor under construction in France. Design temperature 150 million Kelvin. Plasma confined by magnetic fields. Deuterium and tritium nuclei collide. Tunnel, fuse, release neutrons and an energy. If it works, tunneling becomes the power source for civilization. No carbon, no waste. Just quantum mechanics turning hydrogen into helium into electricity. ITER is scheduled to achieve first plasma in 2025. We'll see. Now the dark side, nuclear weapons. Uranium-235. Neutron hits the nucleus. The nucleus splits. Fission releases more neutrons. Chain reaction, bomb. But why does the nucleus split? It's held together by the strong force. You dump energy in by hitting it with a neutron. The nucleus deforms, vibrates. Looks like a dumbbell, 2 lobes connected by a neck. Coulomb. Repulsion pushes the lobes apart. The strong force tries to hold the neck together. Classical physics says the nucleus needs to stretch far enough that Coulomb wins. That's a high energy barrier. Fission should be rare. But it's not. Quantum tunneling. The 2 lobes don't have to fully separate classically. The wave function of the system includes configurations where the neck is split. The probability is small, but it's non-zero. The nucleus can tunnel from the dumbbell state to the separated state. Once it does, the lobes fly apart. Each carries 100 MeV. The whole thing is tunneling. The neutron-induced deformation raises the system energy enough that tunneling becomes probable. Spontaneous fission happens too. Californium, 252, half-life 2.6 years. It splits on its own, no incoming neutron. The nucleus just vibrates into a tunneling configuration and boom. The Manhattan Project physicists knew this. They calculated tunneling rates to figure out how much uranium or plutonium you need for a critical mass. Too little and neutrons escape before causing fission. Too much and it goes off in your hand. Tunneling math told them exactly where the line was. Hiroshima, little boy, 64 kilograms of uranium, 235. Nagasaki, fat man, 6.4 kilograms of plutonium, 239. Different materials, different tunneling rates, same physics. Quantum mechanics built the bomb. Tunneling shows up in medicine, magnetic resonance imaging, MRI, proton nuclear magnetic resonance. You lie in a strong magnetic field. Protons in your body, mostly in water, align with the field. A radio frequency pulse flips the spins. When they flip back, they emit a signal. Different tissues have different relaxation times. That builds the image, but the flip happens because of tunneling. The RF photon doesn't have enough energy to classically excite the proton to a higher energy state. But quantum mechanics lets the transition happen anyway. Tunneling between spin states, the probability is tuned by the magnetic field strength and the RF frequency. Get them right, and the transition rate peaks. That's resonance. Every MRI scan is quantum tunneling, creating contrast between brain and tumor, between muscle and fat, between bone and cartilage. You can see inside a living body without cutting it open, because protons tunnel between spin states. Radiation therapy, cancer treatment, electron beams. The beams need to deposit energy in the tumor, but electrons scatter, hit atoms, ionize them, create secondary electrons. Some of those secondary electrons tunnel through DNA, break the double helix, kill the cell. That's the goal. Kill cancer cells. But tunneling doesn't discriminate. Healthy cells die too. The trick is geometry. Focus the beam, hit the tumor from multiple angles. The tumor gets the full dose. Surrounding tissue gets a fraction. Tunneling is the damage mechanism. Control the beam, and you control which cells die. Proton therapy is better. Protons are heavy. They don't scatter as much. They deposit energy at a specific depth. The Bragg peak. Before the peak, low dose. At the peak, high dose. After the peak, almost nothing. You can put the Bragg peak in the tumor, Spare everything else, but protons still tunnel. They still break DNA. The physics is quantum. The application is life or death. Then there's flash memory. Your phone, your laptop, USB drives, solid-state drives, all use floating gate transistors. The gate is electrically isolated, surrounded by silicon dioxide. Charge stored on the gate changes the threshold voltage of the transistor. Write a bit, inject electrons onto the gate. Tunneling. Fowler-Nordheim tunneling. Apply a high electric field, 10 million volts per centimeter. Electrons tunnel through the oxide. Get trapped on the gate, the charge stays there. No power needed. The oxide is thick enough that tunneling is rare. Data retention 10 years or more. Erase a bit. Apply the opposite field. Electrons tunnel back off the gate. Read a bit. Check the threshold voltage. If it's high, the bit is 1. If it's low, the bit is 0. Every byte on your drive is quantum tunneling holding charge in place. The problem is endurance. Every write erase cycle damages the oxide slightly. Trap states form. After 100,000 cycles, the oxide degrades. Tunneling becomes unpredictable. Bits flip. Data corrupts. Modern drives use error correction codes, wear leveling algorithms, spread the writes across the whole drive, even out the damage. But the fundamental limit is tunneling. The oxide can only take so many electrons punching through before it breaks. SSD lifespan is quantum mechanics fighting silicon dioxide structure. Quantum tunneling isn't some abstract weirdness locked in a physics textbook. It's real. It's everywhere. It's in the sun, in your DNA, in your computer, in hospital machines saving lives, and in weapons ending them. Particles don't care about barriers. Wave functions leak through. Probabilities become events. And every second, trillions of particles in your body tunnel through barriers that should stop them cold. That's the universe. That's quantum mechanics. And there's no going back. So here's what we know. Alpha decay. 1928, Gamow-Condon-Gurney predicted. It matches Geiger-Nuttall. Uranium decays because alpha particles tunnel through a 30 million electron volt barrier with 5 million electron volts of energy. The half-life is 4.5 billion years because the probability is exponentially suppressed. But it's not zero. The math fits every isotope on the periodic table. You can measure it with a Geiger counter. Tunnel diodes, 1957. Eseki dopes germanium to 10 to the 19th per cubic centimeter. Fabricates a 10 nanometer junction. Gets negative resistance. Tunneling current peaks, then drops as voltage increases. Sony manufactures them by 1960. Oscillators run at 5 gigahertz. 50 years later, the diodes still work. Josephson junctions, 1962. Brian Josephson, age 22, predicts Cooper pair tunneling. Supercurrent flows with zero voltage. Phase difference controls current. Anderson and Rowell confirm it in 1963. Clark Deverett Martinis push it to macroscopic quantum behavior in 1985. Nobel Prize, 2025. Every superconducting qubit uses it. Google's Willow chip solves problems classical computers never will. STM. 1981. Binnig and Rohrer at IBM Zurich. Tungsten tip 1 atom wide, held angstroms from a surface. Tunneling current is exponentially sensitive to distance. Scan the tip, map the surface. Atomic resolution. March 16, 1981, they image gold. Nobel Prize. 1986, 5 years. Nanotechnology is born. DNA mutations. Loden proposes it in 1963. Slocum models it in 2021. Protons tunnel through hydrogen bonds. GC pairs have high reverse barriers. Protons get stuck on the wrong side. Polymerase reads the wrong base. Point mutation. Tunneling dominates over classical hopping by orders of magnitude. Enzymes use it. Kinetic isotope effects prove it. Lipoxygenase shows an 80-fold effect. Mitochondrial complex 1 pumps protons by tunneling through hydrogen bond chains. Your cells run on it. The sun burns because of it. Protons tunnel through Coulomb barriers at 15 million Kelvin. Without tunneling, stars don't ignite. Fusion reactors need it. ITER aims for first plasma in 25. Tunneling is the energy source. Nuclear fission, uranium-235. The nucleus tunnels from a stretched dumbbell state to separated fragments. Chain reaction, bomb, californium-252 splits spontaneously. Half-life 2.6 years. Quantum tunneling wrote the Manhattan Project. MRI, protons tunnel between spin states. RF photons flip spins that shouldn't flip. Relaxation times build the image. You see inside a body without cutting because of tunneling. Flash memory. Electrons tunnel through silicon dioxide onto floating gates. Stay there for 10 years. Tunnel back off to erase. Write, read, erase. Every cycle damages the oxide. After 100,000 cycles, it breaks. Your SSD's lifespan is quantum mechanics versus material science. And that's not the full list. Scanning tunneling spectroscopy measures local density of states. Resonant tunneling diodes hit terahertz frequencies. Quantum dot cellular automata use electron tunneling for computation, molecular electronics, graphene transistors, topological insulators, superconducting qubit readout, electron transfer and photosynthesis. Quantum biology is tunneling, olfaction might be, avian navigation possibly, enzyme catalysis definitely, mutation certainly, aging maybe, tunneling is substrate, its mechanism. It's the reason things happen that shouldn't. So what's terrifying? The lack of control. You can't turn it off. Barriers don't stop particles. Walls aren't walls. Build a transistor. Electrons leak through. Write a gene. Protons slip across. Lock a nucleus together. Alpha particles escape. Every engineered system that relies on containment fights quantum tunneling. And quantum tunneling wins. We design around it. High K dielectrics. Error correction codes. Shielding. Cooling. Isolation. But the wave function doesn't care. It spreads. It leaks. It tunnels. The probability is low, but it's never zero. Run the system long enough. Trillions of events per second. Low probability becomes certainty. A cosmic ray hits a memory cell. A bit flips. Your computer crashes. That's tunneling. A proton shifts in a GC pair. DNA polymerase makes an error. A cell turns cancerous. That's tunneling. An alpha particle escapes a uranium nucleus in a granite countertop. Hits your lung tissue. Damages DNA. Radon exposure. That's tunneling. Or flip it around. What's terrifying is how much we depend on it. No tunneling. The sun goes dark. Enzymes stop working. Cells die. You die. Civilization collapses. Life never evolves. The universe is cold. Hydrogen floating in the dark. Tunneling is the narrow probability bridge between nothing and everything. Particles that shouldn't cross do. Reactions that shouldn't happen do. Structures that should be stable aren't. And all of it runs on one fact. Quantum mechanics doesn't respect barriers. Wave functions leak. Probabilities become outcomes. Particles appear where they shouldn't be. And there's nothing classical physics can do about it. Here's the final piece. Quantum tunneling is time dependent. The particle doesn't slowly dig through the barrier. There's no travel time. The wave function exists on both sides simultaneously. Then you measure. Collapse the wave function. The particle is on one side or the other, but before measurement, it's both. Schrödinger's equation is deterministic. The wave function evolves predictably, but the measurement outcome is random, probabilistic. You can calculate the odds. You can't predict the result. Run the experiment 1 billion times. Half tunnel through, half bounce back. But which one tunnels on trial 500,000,001? No answer. The universe doesn't know until it happens. That's quantum mechanics. That's the foundation under everything. Atoms, stars, life, technology, all built on a mechanism that fundamentally refuses to tell you which side of the barrier the particle will end up on until you look. And by the time you look, it's already decided. You can't rewind. You can't check. The past is probabilistic. The future is determined by dice that aren't dice because dice have hidden internal states that determine the outcome, and quantum mechanics provably doesn't. Bell's theorem guarantees it. Local hidden variables don't exist. The randomness is real, ontological, woven into the structure of reality. And tunneling is the clearest example. A particle approaches a barrier. Will it tunnel? Ask quantum mechanics. Answer, maybe. How helpful. But that maybe is the only answer the universe has. There is no deeper layer, no hidden mechanism. The particle doesn't know if it will tunnel until it does, and then it did, or it didn't. And you run the experiment again. So what does that mean? It means every decay event, every mutation, every leakage, current, every electron in every device, every proton in every cell is riding on a probability that exists as a number in a wave function until the moment it collapses into reality. Your computer works because electrons tunnel through gates in precise percentages. Your cells live because protons tunnel through enzyme active sites at tuned rates. The sun burns because a tiny fraction of hydrogen nuclei overcome barriers they shouldn't. All of it is balanced on exponential decay functions and Schrödinger's equation and boundary conditions at infinity. Change the barrier width by an angstrom. Change the probability by an order of magnitude. Change the outcome. Uranium decays slow because the barrier is thick. Polonium decays fast because it's thin. Your SSD lasts 10 years because the oxide is thick enough. Make it thinner. Faster writes. Shorter lifespan. Make it thicker. Slower writes. Longer lifespan. You tune the barrier. You tune the tunneling, and reality tunes you. DNA evolved to tolerate a certain mutation rate. Too high. Can't maintain genetic information. Too low. Can't adapt. The tunneling probability of protons through hydrogen bonds in DNA sits at the sweet spot. Enough mutations to evolve, not so many you dissolve into cancer. That balance is quantum mechanics filtered by 4 billion years of selection pressure. Life exists in the tunneling regime where the wave function leaks just enough, and now we've learned to engineer it. Josephson junctions tune phase differences with microwave pulses, control qubits. Build quantum computers, STMs push atoms one at a time, build molecular machines, fusion reactors aim plasmas at 100 million Kelvin, chase tunneling cross-sections, flash memory cycles, oxides 100,000 times. Wears them out, replaces them. Tunneling is the tool and the limit. We can't stop it. We can only shape it. And that's the state of physics today. Quantum tunneling is no longer a curiosity. It's infrastructure. The sun, your DNA, your phone, hospital machines, power grids, communication satellites. All of it runs on particles punching through barriers that should stop them. Classical mechanics failed a century ago. Quantum mechanics replaced it. Tunneling is the signature, the proof, the mechanism that separates quantum from classical, and every day we push it further. Smaller devices, colder temperatures, higher barriers, faster tunneling, until we hit the noise floor, until decoherence wrecks the wave function, until thermal fluctuations smear the probability. But we're not there yet. We're still writing exponential curves. Moore's law is dying, but quantum scaling is starting. Qubits double slower than transistors, but they're doubling. Error correction improves. Gate fidelities rise. Tunneling gets cleaner, more controlled. We're learning to sculpt probability distributions like engineers sculpt metal. And that's the power, and that's the terror. Because once you can control tunneling, you can control chemistry, biology, energy, information. All of it runs on particles moving through barriers. Master tunneling. Master the world. But the universe isn't done. There are types of tunneling we haven't seen yet. Klein tunneling in graphene. Particles approach a potential step. In normal materials, they reflect. In graphene, they pass through perfectly. The barrier becomes transparent. That's relativistic quantum mechanics meeting two-dimensional materials. Another type, dynamical tunneling. Classical chaos meets quantum mechanics. A particle sits in a stable orbit. Chaos would kick it out, but chaos is classical. Quantum mechanics has tunneling. The particle tunnels from the stable region into the chaotic sea, or vice versa. Experimental signatures show up in cold atom systems, in Rydberg atoms, in microwave cavities. The particle doesn't cross a spatial barrier. It crosses a phase space barrier, from order to chaos, from chaos to order. By tunneling, then there's vacuum decay. Theoretical, not observed. If the Higgs field sits in a false vacuum, it could tunnel to a true vacuum, lower energy state. The tunneling would nucleate a bubble. The bubble would expand at light speed. Inside the bubble, physics is different. Particle masses change, forces change, atoms fall apart. The bubble eats the universe. The probability is low, extremely low, but it's not zero. Run the universe long enough. Wait 10 to the hundreds of billions of years, maybe longer. The Higgs field tunnels, everything ends. Not a heat death, not a big rip, vacuum decay. Instant, unstoppable. Driven by quantum tunneling on a cosmological scale. We don't know if it's real. We don't know if the vacuum is false or true, but the math says it's possible. And if it's possible, tunneling will eventually make it happen. That's the ultimate terror. The universe itself is metastable. It could tunnel to a lower state. And when it does, everything we've built, everything we've learned, everything that exists gets erased by a quantum fluctuation, a probability, a leak in the wave function of the cosmos. That's quantum tunneling, alpha decay, tunnel diodes, Josephson junctions, STM, DNA mutations, enzyme catalysis, solar fusion, nuclear fission, MRI, flash memory, semiconductor leakage, quantum computing, nanotechnology, life, death, energy, information, all built on particles crossing barriers they can't cross, all running on probabilities that shouldn't add up, all powered by wave functions that refuse to stay on one side. Classical physics says no. Quantum mechanics says yes. And reality listens to quantum. Every second, every atom, every star, particles tunnel, barriers leak, probability becomes certainty, and there's nothing you can do to stop it, because the wave function doesn't care what you think is possible. It spreads, it leaks, it tunnels. And on the other side of every barrier, something that shouldn't be there appears. Without permission, without warning, just quantum mechanics being quantum mechanics. And that's the universe we live in, whether we like it or not.